Anyway, thanks to Rajiv and organizers of the meeting, of course, for inviting us here. And I'm going to talk about laser Wakefield accelerators and radiation sources based on these accelerators. The work being carried out at University of Strathclyde. And just to let you know where we are, Strathclyde is in Glasgow, in the middle of Scotland. And Scotland is an interesting place for many reasons, apart from Bob coming from somewhere around here. And that James Clerk Maxwell was born in Scotland and is actually buried here in Dumfriesshire. A couple of other quite important things that occurred in Scotland, for example, the measurement of the world's density, and also famous geologists and scientists like Lord Kelvin. Even though he comes from Northern Ireland, he spent most of his life in Glasgow. James Hutton showed that the world wasn't just a few thousand years old, but actually millions of years old by looking at the non-conformity of strata in the world's crust. He showed that strata that sat on top of each other demonstrated an age which was much, much older than people had thought at that point. And Strathclyde is also part of something called SUPER, Scottish Universities Physics Alliance. It's a collection of universities, physics departments, which sort of combine forces to train students and to work together, collaborate. And actually, some of the work that I'll be presenting is part of this collaboration between these universities. And I'm going to be talking about basically how to harness the electric fields that can be created in plasma by separating charge. We can separate the charge using electrostatic forces of energetic charge particles or laser pulses, as we've already heard. Wonderful introduction. I'm going to be focusing on some of the experimental work that we've been doing and some theoretical work as well in how to make these accelerators have parameters which are unique compared with conventional accelerators. And even though they're generally quite low charge accelerators, they can have extremely short electron bunches, as you'll see. And the medium is just plasma. Plasma can be either in a gas jet, ionized by a high power laser, or preformed in a channel such as this one here. So these beams can be taken out and passed through external devices like undulators, or they can be used also for radiotherapy and so on. I'll tell you a little bit about that. But this will be a very brief discussion. And one of the things we're developing theoretically, we want to do experimentally, is the ion channel laser. This is a form of free electron laser which uses electrostatic forces of an ion channel as a wiggler or an undulator. And I'll also be talking about how you can produce very short wavelength radiation, even up to several MeV, by exciting large transverse oscillations of electrons in these plasma channels, in the bubble, the accelerating channels. And finally, I'll talk about facility. So as we've seen before, the interest in this, in using plasma, is because you can have very much higher accelerating gradients. And accelerating gradients, for example, at CERN, around 10 MeV, sorry, 10 megavolts per meter, as Bob mentioned, and even SLAC is about 20 megavolts per meter. And the maximum field that an RF cavity could withstand is about 100 megavolts per meter. So a plasma separating charge, even a modestly dense plasma, you can have fields up to teravolt per meter. So in principle, you could put CERN in a room like this if you could somehow keep track of the charged particles over a long length. So that's what part of the challenge, as we've heard. And so it turns out that the structures that you can make in plasma by pushing charged particles, the electrons out of the way, ions remaining stationary because they're much heavier, is very similar to a conventional accelerator. The only difference is it travels along close to the speed of light, which is an advantage that you can then track the charged particles over a long length. And so part of the challenge is to separate the charge and also how to ensure that the structure moves along close to the speed of light, because charged particles, light charged particles accelerating in these structures have trouble actually at a speed faster than the structures and will outrun these structures. So that means that the useful time over which you can apply the accelerating fields is limited by this slightly lower velocity of the structure. So you can speed up the structure by using a charged particle beam. So if you use a highly relativistic charged particle beam, as has been done at SLAC, you can then make a structure which then can travel along at a velocity much closer to the speed of light, and therefore you can track the particles for a longer length. So therefore you can make accelerators in one length rather than thinking about having several stages. So this shows you this is a 1 GeV accelerator. So these can be extremely compact. Of course, the power supply is large. The laser can be quite large. So so some of the motivation behind this is that if you look at the growth of the center of mass energy of accelerators, growing about 1 order of magnitude every 10 years. And this is because of several of the introduction of new ideas, new innovation, basically. And what's interesting is not so much the increase of the energy that's available, but maybe developing new technologies which spawn new uses for this technology. So actually, our interest is not so much in going up this line, but is what can we do with the technology horizontally here by refining it. And we'll be talking a little bit about that. And we've heard that the ponderomotive force of plasma electrons inside a high-power laser can drive the electrons out of the center of the laser beam, the path of the laser beam. And so this is not these extremely high intensities where the electrons will flow into the center of the laser pulse. But the ponderomotive force will drive the electrons out of this way, and the restoring forces of the ions left behind will cause the electrons to oscillate plasma frequency, and this produces a density modulation in the plasma, or a wake, and that's hence the name Wakefield accelerator. And as we heard, John Dawson and Satoshi Tajima in 1979 proposed the idea of the Wakefield accelerator, how exploiting this structure. And of course, as Bob mentioned, as Bob said, you can also drive the structure by resonant self-modulation of a long laser pulse or a series of very short pulses. There are several ways of driving this, even with a laser beam. You can also probably do with a particle beam if you have many particles accelerating particles inside the plasma. For example, the proton-driven Wakefield accelerator at CERN, the AWAKE project, which operates by splitting the proton beam into segments. And the group velocity of the laser beam, and you can associate the Lorentz factor with this group velocity. and then you can calculate the maximum energy that's available. So one of the interesting aspects of this is that the field can be extremely high. Field is just really proportional to the square root of the density here. So this can be up to teravolt per meter for densities which are just between 10 to the 19 to 10 to the 20 electrons per centimeter cubed. If you want to build but of course the wave itself travels at this lower velocity and therefore sets a maximum energy that you can accelerate, which is just related to this Lorentz factor associated with the group velocity of the laser, square of this, and also the field, the normalized vector potential of the laser field. So if you want to go to higher energies, you have a choice of either going to lower densities, so you make the wave travel faster, or going to higher laser intensities, so you make a slightly larger bubble. And therefore you have a longer time over which you can accelerate particles. And it's quite interesting to have a look at what's been demonstrated already of these accelerators. And just by changing the density of the accelerator, one can have the energies which can range from just a few MeV to a few GeV. And in principle, you could make a 100 GeV accelerator just by lowering the density. But of course, one of the challenges is to produce these wakes, you also have to match, as Bob mentioned, you also have to match the laser pulse to the structure that you're making. That means you have to go to lower density, where these bubbles are larger. You need very, very large lasers. So you need kilojoule lasers, or maybe larger kilojoule lasers, to produce a 100 GeV accelerator in one step. So the maximum energy that's been achieved up to now is about 4.5 GeV with a relatively modest laser. And these lasers are sub-petawatt lasers. So the 4.5 GeV accelerator is, I think, has used about a 300 terawatt laser to use this. So in principle, you can have this in any laboratory. So it means also that these accelerators can be situated in relatively small laboratories. So we've had a bit of the history already, so I won't go through that again. Just to say that these structures here, simulation of the structures, are actually quite good accelerators because the fields are extremely uniform in these accelerators. In this so-called blowout or bubble regime, where the electrons are fully expelled from these regions, so actually, these structures are of the order of 10 to 30 microns for the densities that allow 100 to 1 GeV or few GeV accelerators. So, because they're so small, because the structure is so small, it turns out that the properties of the beams inside these structures can also be quite good. And particularly the bunches that you can accelerate in these structures can be extremely short and very compact and have actually quite a good transverse momentum spread. And therefore, in principle, you could build a laser-driven Wakefield accelerator suitable for a free electron laser on a bench top. These are literally centimeter-long accelerators with of course, larger lasers. But in principle, you can do this because the mittance is small enough, the bunches are short enough, and the charge is high enough, so you can have peak currents of around 10 kiloamperes, and energy spreads approaching around 1% at 100 or 200 MeV. So in principle, you can scale this up to several GeV and have an energy spread which is sufficient for driving, sufficient quality for driving a free electron laser. So this is one of the challenges, which I'll tell you a little bit about how to get there. It's actually quite a challenge, even though it sounds quite simple. So important part of understanding this is using PIC codes, particle and cell codes. This just shows you modeling using 2D model of the Wakefield accelerator. And here, just to show that, as we heard previously, in this very highly nonlinear regime where you get this bubble forming, electrons can be injected into the plasma from the background plasma, into the bubble from the background plasma, and extremely short bunches can be injected. And this is because like you described as a wave breaking, but this bubble velocity can change, and the sheath of a bubble, which is formed by electrons streaming around the edge of the bubble, the velocity of the back of the bubble can increase and then can decrease, which eventually allows electrons to be self-injected into the plasma, and this very short electron bunch can be injected. And what's interesting here is these electron bunches come in with some transverse momentum, so they will naturally oscillate in the bubble because it's a centralized potential. This is literally an ion channel as far as the electrons are concerned, and they will just oscillate transversely. And you can see here the start of these electrons will accelerate very rapidly. So the bubble has a Lorentz factor around 10 or so, between 10 and 30, and electrons will have a gamma factor very, very quickly, getting on to the hundreds. And these transversely oscillating electrons will radiate, just as in a wiggler. And the only difference with a conventional wiggler is that the electrons are accelerating longitudinally as they oscillate. And you can see here that these electrons are occupying an extremely small volume. So the density of electrons that are oscillating can be higher than the critical density for the laser beam that's propagating in it. So the densities inside these tiny, tiny electron bunches can be of the order of 10 to the 22, 10 to the 23 electron cubic centimeter. So they're very, very high current density, extremely high current density. The total current, as I said, peak current can be of the order of 10 kiloamperes or more. So this really makes them suitable for a radiation source. So one of the challenges is of course, how to control this acceleration. We'll already hear from Zulf about some of the stuff that he's been doing. But so this is a big challenge, because you have these electrons which are oscillating transversely here, and the electrons come out. They really depend on the stability of the whole system. So for the electrons to come out, for example, even at the same angle, because the energy is delivered to the plasma at a constant rate, while the electrons accelerate, and at some point get depletion of the laser beam, as we've heard, and the bubble structure will disappear. And it's a challenge to design a system where the electrons will come out with the same transverse momentum, so they point in the same direction. This is quite a challenge. And you can by just varying the density of the plasma, or the vector potential of the laser beam, the intensity of the laser beam, therefore the vector potential, you can then scale, you can adjust the size of the bubble. So you can adjust some of the parameters simply by varying either the plasma density or the vector potential, and which changes the velocity of the bubble and therefore all the other parameters. So to investigate this, we set up this project in 2002, I think, 2001. Included Zulf in the early days as well. And one of the major results of this project, it's called Alpha X, was one of the experiments led by Zulf in fact, at Rutherford, where controlled acceleration was demonstrated. And in Scotland, we set up this beamline to try and investigate this acceleration, controlled acceleration, and to try and investigate the feasibility of making a free electron laser out of this. And also radiation sources. So much of this is just a conventional beamline with quadrupoles for focusing the electron beam to match it to the undulator, and also diagnostics for measuring the various parameters of the electron beams. So the most basic component of the accelerator is the plasma. So this is usually a gas in the form of a gas jet or in the form of a gas cell. And relativistic self-focusing, as we heard, can allow the laser beam to guide over a long length. But rather than diffract over the Rayleigh length, the laser beam in fact guides over a very long length. So this shows you here that the laser, this is a gas cell here. This is a 10 joule laser. Probably more around like 3 joules there. This is a 1 GeV accelerator, and the laser beam will guide over 4 centimeters through the self-guiding. So it actually can be quite a stable setup. Of course, it depends very much on the laser parameters. So the laser parameters vary from shot to shot. The parameters of the accelerator will vary. But it is possible to produce these accelerators just simply by having a gas cell focusing these laser beams into the gas, and out comes a good electron beam. A more usual medium is a gas jet, or not usual, but common in the early days at least. And just in 2 millimeters, you can produce about 300 MeV accelerator. So, and the self-guiding also occurs here. So, if you want to go to higher energies, generally you would use a preformed waveguide. This is just a waveguide formed in a hollow capillary with electrical discharge, and one can then guide the high-power laser over a long length without needing to go into this relativistic self-guiding regime. This type of structure has been used to produce several GeV beams already. So the parameters, just to show you that the parameters can be quite good. So this shows you that normally the energy spread of the beam is a few %, but possible by operating very close to the threshold for injection of electrons into the plasma to go down to around 0.3. I think our smallest relative energy spread at about 130 MeV is about 0.3%. So 0.3% also, if you can further accelerate this to GeVs, this is really suitable for a free electron laser. And the charge is sufficiently high for the beam to be to have about 10 kiloampere peak current. And not only that, but the average energy spread from shot to shot can be quite good if the laser is stable. So you can operate this almost like a conventional accelerator even now. But the beams are relatively divergent, and therefore it is actually quite a challenge to transport the beam. So this is the next challenge in being able to use these beams. But this just shows you that with a very well-controlled system, one can actually have quite a good pointing stability. So these electron beams will the angle that they come out of the relative to the laser propagation length, distance, direction, can vary by the order of 1 or 2 milliradians. So this means that if you pass these through a miniature focusing system, these are just quadrupole magnets here, one can then transport these beams over a long length. So in principle, you can get them through an undulator, and they become quite usable electron beams. And you can even get, if you use a capillary, you can even get to a pointing stability of around 0.5 milliradian. So this means that really these beams will go in the direction that you want them to go. So therefore, they become quite quite useful. And of course, an important parameter in terms of using these and delivering them to where you want to use them is the transverse momentum spread, which is characterized by the emittance. And this just shows you, this is actually measurements that were carried out in Scotland, where we were able to show that the emittance, these are the measured emittance of a 1 pi millimeter milliradian. This is equivalent to 1 micron radiation in focusability. And in fact, this is just really an upper limit. So I think the emittance is around 0.3. So this is already quite a good emittance beam. So in spite of the fact that you've got these huge forces in the accelerator, you can have quite a good emittance because the source size is incredibly small. The source size of the electrons in the accelerator is of the order of 1 micron or less, maybe even half a micron. So these are actually quite useful beams. And it's also possible to produce more than one beam in these accelerators by controlling, or not controlling, for that matter, the laser beam in the accelerator. One can produce 2 beams, or maybe even more beams. So you could produce, for example, 2 beams with the same energy if they injected simultaneously. And so what we've done here is through this method of so-called pepper pot measurement method, one can, for example, produce 2 beams with different energies going in the same direction, or 2 beams with the same energy going in different directions. So it shows you that the accelerator can actually be used by controlling the injection, or not controlling the injection for that matter. One can produce beams of quite interesting properties. Because the structures are of the order of 10 microns in size, the electron bunches can be incredibly short. So it turns out that, and these are measurements that have been carried out by measuring the coherent transition radiation of the electron beams going through a thin foil. And by measuring the spectrum of this, one can deduce the electron bunch shape and length. And we were able to show here that the electron bunches are the order of 1 femtosecond at the source. And they can have some substructure. For example, you can have more than 1 electron beam bunch being injected into these accelerator. And they can also have energy chirps. So that means that if you want to ballistically compress them, one can just introduce a drift space. And in this case, these bunches are slightly compressed as they propagate because there's a small negative energy chirp. And because these bunches are so short, when you pass them through the foil, they actually produce infrared radiation. And a single cycle infrared radiation pulse, which is coherent transition radiation, actually can have megawatt peak power. So in fact, these beams, just by simply passing them through foil, can become interesting sources of radiation. So, because it's very difficult to make single cycle pulses in the middle of the infrared. In fact, it's relatively easy to do it in the terahertz frequencies, the 1 terahertz range of frequencies, but the 100 terahertz frequencies, it's quite difficult to make these single cycle pulses. So even though this hasn't been used, this just indicates that these bunches of electrons produced by these laser accelerators actually can be quite useful radiation sources for applications. Of course, the challenge then is to stick an application on the end of the beam. So, so what we've been doing to try and understand why we get such short electron bunches, we've been looking at how the electron bunches are injected into the accelerator. And as I said, in this bubble regime, these electrons will be accelerated, that the electrons form a sheath which defines the accelerating regime, this plasma bubble. And the question is, how do they get injected into the back of this bubble? So there are some theories which show that by changing the velocity of the bubble, we know from the simulations, for example, that as the laser beam exchanges energy with the plasma, the velocity of the bubble will change, and therefore you get spontaneous injection of the electron beam. But that wouldn't normally result in very short electron bunches. So we were trying to understand why this is the case. If you look at the theory, injection theory, you can see that you get this so-called wave breaking. And it turns out that the wave breaking threshold for injection is quite far away from the experimental parameters for people who have observed electron beams. So there must be something else going on. So what we're trying to understand is how do these electron beams get injected here? It turns out that the buildup of the plasma at the back of the bubble here acts to locally change the potential, and the electron beams are kicked into the back of the bubble, as in the first simulation that I showed you. So this is a very simplified model here, but shows you these electron beams can then be injected into the back of the bubble. If the bubble is expanding and there's a variation of the charge density at the back of the bubble, so the question is why do you get charge density variations there? And that's because there's this bifurcation of current that flows around the back of the bubble at this point, and the amount of charge that's divided at that point can vary in time. And the variation can be very, very rapid. And these are simulations which show that would support this hypothesis here, show that you can get injection of more than one bunch just by variations of the potential at the back of the bubble. This shows you regions where you'd expect to have injection, and these coincide with these double injection of these two double electron bunches. And these can be extremely short. As I said, these can be of the order of 1 femtosecond. So it's possible we've been continuing to work on this area, and by controlling the plasma density, one is able then to go down to about 300 attoseconds. So this is really work that's being theoretically carried out using 2-dimensional and 3-dimensional modeling. One is able to then go down to about 310 attoseconds RMS bunch length. So one of the interesting aspects of the accelerator is what happens to the laser energy. Now we know that the energy has to deliver, the laser beam has to deliver its energy to the plasma at a constant rate. Where does this energy go? Well, we've heard from previous talks that the energy is stored in the plasma. The oscillating electrons in the plasma and the field exchange their energy, so the energy stays in the plasma wave. And we know also that in this self-injection regime, that a beam of high energy electron beams come out. The question is, where does all this energy go? If you do the calculation, let's say taking a 1 joule laser, which is the sort of lasers we have at Strathclyde, the electron beam the high energy electron beam that comes out has only a total energy of about 1 millijoule. And therefore, what happens to the other 999 millijoules of energy? It turns out that the laser beam deposits about half of, our experimental parameters, deposits about half of its energy into the plasma. And the question is, where does that energy in the plasma go? We know the laser comes out because you measure the transmission of the laser beam. And it turns out that the electrons actually come out as the plasma wave, because the plasma wave that you form is a coherent structure. This coherence of the structure is actually maintained, and it comes out as jets of electron beams. Actually, and these are, so you can imagine that the plasma bubble, the amount of charge in the plasma can be several hundreds of nanocoulombs. So all that charge that's being pushed out actually comes out as coherent. Almost all the charge comes out as coherent beams. It doesn't thermalize, it just comes out as a beam. And it turns out that it comes out as relatively low energy beams. These are electrons which are not trapped in the bubble, but which form the sheath. And these beams can come out as jets of electrons of very high charge. So you can imagine that you got about 1 or so millijoule of electron beams at the high energy jet here, and you can get tens of nanocoulombs, maybe even 50 nanocoulombs of charge coming out of these jets. They don't only come out in the forward direction, they can also come out in the backward direction, because this coherent structure, these the forces, as I said, are of the order of 100 gigavolts per meter, teravolt per meter, very high density. And this huge force actually pushes the electrons out of the plasma eventually. Even the electrons which form the sheath get ejected. And the bubble will disappear, in fact, in this process. So these beams come out, and it turns out that the beams can actually have energies of several MeV. And if you're not careful in measuring the forward electron beams, you can pick up some of these side electron beams, and you can mistake them for electrons that have been injected. So when you talk about a Wakefield accelerator, you have to be a little bit careful about how you describe the beams. And in fact, in some of the early experiments that were made, in the so-called Dream Beam papers, measured charges which they claimed to be of nanocoulomb charge. And they almost certainly picked up some of these low-energy electron beams, bunches, beams which were not injected into the Wakefield accelerator, but they're still coherent beams. And also, this is a challenge because these electron beams, this just shows you the bubble here. And these families of electrons which form the sheath. You can see here that these electrons which forming the sheath will come out in these wakes or the bows. And these electrons will come out of these at these angles here. So this just shows you two groups of electrons which are coming out. These are color-coded here for high energy electron beams. So these are consistent with our measurements that we've made at Strathclyde, which I'll show you in a minute. But these come out into these angles of about 45 degrees. So you get this big beam of electrons coming out at about 45 degrees with charges of the order of maybe even 10 nanocoulombs. So the current, peak current of these beams can be of the order of 10 kiloamperes, even though they are coming out. And so you're talking about nanocoulomb beams with 10 kiloampere charge. So of course, the energy spread can be quite broad because it really depends on the history of these electron beams as they're propagating around here. And but they definitely come out with these beams. So, and in fact, they not only come out in the forward direction, they come out also in the backward direction. So you can see here, these are simulations which shows that some group of these electron beams is like a slingshot. So you can imagine that the central potential of the bubble then pulls the electron beams out that are going around, and they get pushed to the side like a slingshot. And some of them even there's even a slingshot in the backward direction. So some of these electrons, they'll come out, and these are relatively lower energy. These are a few hundred keV, but still with charges of the order of nanocoulombs. So these are simulations which show this. This is in the laboratory frame here. So these electrons then are propagating out of these angles, these 100 keV. The forward-directed ones, this is in the bubble frame here, are propagating out at this angle of about 45 degrees. So that if you focus the electron beam, if you focus the laser beam into the plasma here, you get this cone of electrons coming out. So this is actually quite interesting, because if you want to build a linear collider out of these, you have to think about where do all these electrons go. Using a preformed capillary to guide the electron beam, these nanocoulomb charges, 10 to even 50 nanocoulomb of charge beams, which can have energies up to 100 MeV. These can actually be quite high energy beams with huge amounts of charge, can come out. And if you have a structure around there, these these consist of 10% of the laser energy. That energy is deposited somewhere. So that's one of the reasons why people lose their equipment in the vicinity of these accelerators, because these beams will hit everything, and they produce bremsstrahlung, and of course they will kill all the electronics. So it's not only the high electromagnetic pulses produced by the presence of the bubble and disappearance of the bubble, but also the beams that come out, these coherent beams that come out. So that's quite an interesting study. So these are real experiments that we've done, where the laser comes in and we've been able to measure in these various directions. So you can see here, these are what these beams look like in reality. Some of these, I can't remember which ones are single shots, but this is this is single shot measurements. And you see these beams that come out of huge sprays of electrons with energies of nanocoulombs, and also in the forward direction. Let's see which one is the backward direction. Anyway, these are all in the forward direction, and you can measure these. And it turns out that these beams have energies of several MeV, and they can be quite useful. And in the backward direction, you get this beam of hundreds of keV, so 200 keV electrons, which come out in this cone of about 15, 30 degrees. So you have, and this is it takes off quite a lot of energy of the laser beam. So if you have optics behind there, you have to think about that. These electron beams will hit the optics behind there. So this becomes a practical consideration when you build these linear colliders. And actually, nobody's really thought about this. And so we've done a whole lot of simulations, and you can see here, by varying the laser beam energy, density, etc., you can get very complicated structures. And these structures, even though the plasma is completely symmetrical, it picks up a whole lot of, there's a symmetry breaking in this whole process here, and you can get these very, very interesting structures. In fact, we observe these structures in experiments. And also, the sort of charge that you're producing accumulates the longer your accelerating structure is, the more charge you produce. So it shows you here how the charge can be. This is nanocoulomb. If you increase A naught from 1, let's say, to 8, you can get 70 nanocoulombs of charge after just half a millimeter of propagation. And here, if you increase the density to high density, for example, to 4 times 10 to the 19 electrons, you can get 20 nanocoulombs of charge. So these are MeV beams with these high charges and high peak currents of the order of 10 kiloamperes. So we've been able to measure these, directly measure the angle, because there's a correlation between energy and angle. And we've even been able to show that you can use these, because these are actually very divergent beams. In principle, you could design magnetic optics to take the beams and use them. But this just shows you, if you just place, this is a hard drive controller, you just place the hard drive controller in the presence of the beam, and you were able to actually take a single shot measurement of this. So these are, and if you think for fusion studies, for example, you could use these sources as sort of backlighters in a sense for beams. And anyway, but these are just very simple measurements here, multiple shots or single shots. So you can actually get pretty good measurements. So 11 minutes left. Okay. So we've taken these beams just to show you what we've done with these beams. We've also taken these beams out, put them through undulators, so we're able to produce undulator radiation. That's quite interesting here, because here you've got a 1 femtosecond electron bunch. And so this is effectively, as far as the radiation process, almost a delta function. And okay, it's still longer than the wavelength of the radiation, so the coherent emission won't occur. But the bunches of these pulses of incoherent synchrotron radiation are also very short. You're talking about, in this case, this is 120 nanometer radiation. We've measured down to about 60 nanometers. But these turn out to be tens of femtosecond UV pulses. And if you go to shorter, if you go into the water window, for example, around 200 EV, 400 EV photon energy, you're talking about pulses of light, even if they're incoherent, of the order of 1 femtosecond or 2 femtoseconds. So just by using a simple undulator, you can produce radiation sources which are as good or better maybe than some of the high harmonic generators, which have relatively complex setups. Anyway, so just this shows you that make these measurements. And if you can get bunching, get a coherent component in the bunching, one can then produce a coherent source, okay? And this shows you that we've had a look to see if we can see coherence in the undulator, which we didn't see coherence passing the electron beam through an undulator, a 100-period undulator, which you should see gain, but you need a very good transport system. So this really indicated for us anyway that we need to develop a very good source. But one of the things we're quite interested in is how to get rid of the undulator. So we've developed a theory now for the ion channel laser, the ion channel free electron laser, where an ion channel, which is an evacuated channel of electrons, background of ions, and electrons which come in, and as I told you, this betatron oscillation would give rise to the radiation. In fact, it turns out that this type of system can operate quite happily as a free electron laser. We were able to show that for large amplitude oscillations, you can have a free electron laser with a very, very high gain. So this parameter here, which defines the gain of the free electron laser, is about 1% here. This is much, much larger than you get in the conventional free electron laser. So it shows you by having a very strong, a very large amplitude oscillation, one can get a very high gain in these systems. So this just shows you the standard theory for the free electron laser. We're able to develop a set of equations which are equivalent to the free electron laser with an added parameter, a space charge light parameter, which takes into account this added degree of freedom, which is the amplitude of oscillation in the channel. And okay, and we can do, we've done the steady state theory, we've done the time dependent theory here. It shows you can get very short pulses, which operate in the superradiant regime. So the question is, can you make this practically? Well, this shows you the first steps towards this. So if you fire the high power laser into the plasma, you get this bubble, as I said. And these electrons which oscillate here would usually, the oscillation amplitude would usually die away, and they would produce they produce the so-called betatron radiation with photon energies of the order of few keV to few tens of keV. And what we noticed in some experiments is that actually we could produce much, much higher photon energy beams. And the question is why that was happening. And it turns out that these electrons, which are trapped inside which oscillating, the betatron oscillating electrons here, are oscillating in the presence of the laser field at the back of the bubble, because the laser beam propagates in its own channel, it propagates in its own waveguide, which is the bubble. So the laser beam group velocity will be traveling at a velocity which is comparable with the bubble. In fact, it's equal to the bubble velocity. That means that the electron beams can catch up with the bubble because the laser beam is not propagating in free space. Okay? So it means it can, because if it's in free space, then of course the electrons would never catch up with the laser beam. So they can catch up, and at some point, the Doppler downshifted, because if they're traveling in the same direction as the laser beam, the Doppler downshifted laser field, which is seen by the electrons traveling in the same direction, will match the natural oscillation frequency of the electron beam in the plasma, in this ion channel here. And at some point, the laser beam frequency will drop to such a frequency that it'll come into resonance with the laser field, and it can pick up a huge amount of transverse momentum. This is something called direct laser acceleration as well. So that means that the electron energy can increase because of the transverse field, directly because of the transverse field of the laser beam. So, and of course, people have been thinking about that, but this is a direct demonstration of this direct laser acceleration. And it's in a controlled way. So you can express this as a nonlinear harmonic oscillator here, driven on harmonic oscillator with a damping term, which depends on the energy, the relative energy, the gradient of the energy of the beam. Yeah. So it turns out that at the center of the bubble, where this gradient goes to zero, the damping the oscillation will also go to 0. And at that same time, you can come into resonance. So this shows you here that you can come into resonance with the field. Anyway, and you can then pick up this large amount of transverse momentum. As you can see here, the amplitude will increase, the transverse momentum will increase, and the total energy. But what's interesting here is this transverse momentum, the normalized transverse momentum, which is given by this parameter A beta, will increase, and the radiation spectrum of coming out of this thing will increase. Because it's just like a wiggler. So these experiments, we've done experiments to investigate this. This shows you in a plasma capillary here, we were able to get to close to 1 GeV beams, actually quite good quality beams. This was done at Robert Appleton Laboratory. And we were able to measure these spectra. So of course, these transverse oscillations, just like a wiggler emission. So we know from the wiggler theory that this transverse momentum parameter A beta, which is the K parameter for a wiggler, the whole number of harmonics of the frequency oscillation that you produce, it's very nonlinear motion, it goes as the cube of this parameter. So if this parameter can be of the order of 100, so you produce the millionth harmonic. It turns out that if you lock the oscillation frequency to the laser frequency of 1 eV photons, you're producing photons which are the millionth harmonic of that. So you're directly converting 1 eV photons to MeV photons. It turns out that this is the case. This is the critical frequency for this synchrotron spectrum is around 450 keV, but the tail of this stretches out to MeV photon energies. So it's quite interesting that just by firing a laser beam into plasma, without having any Bremsstrahlung or any collisions, you could directly produce MeV beams. And you can also estimate the scaling parameters show that you could maybe get to 10 or even more MeV photon range. And of course, the radiation they produce comes from a very small source size, and I'm pretty sure that Zulf is going to talk about this. But you can use phase contrast imaging, which is interesting in its own right, but it can also be used to work out the size of the source. And by looking at these phase contrast images, here one can then work out the source size. It turns out the source size is of the order of 7 microns, which is equivalent to the amplitude of oscillation for this particular case. And we've been able to show, because one of the things we were trying to find out is whether we can use this for biological imaging and so on. One can actually get a resolution for this phase contrast imaging down to about 2 microns. And what's interesting for this resonant betatron oscillation is that if you compare them with conventional synchrotron sources, they have a peak brilliance, which is equivalent to a third-generation synchrotron source, but in a range where they're not available. So these electron beams can also be used to this is just to show that we do other work. We can use these electron beams. So this is studies for radiotherapy to use a very high energy electron beam for radiotherapy. So these are dosimetry studies. I'm not going to say anything more about that. Just show you that these beams are really controllable. So this is the simulations, and these are measurements. Okay, so these beams are really usable. These are measurements done in a phantom. This is a standard method for measuring the so I'm going very briefly. I'm not going to say anything about these, just to show that at Strathclyde we are have a broader activity than just what I'm doing. So we have theoretical work being done by Zhengming Sheng, looking at ways of making exotic type of wigglers and controlling injection, et cetera, optical modulation, and also Paul McKenna's group, and looking at how this is an ion acceleration laser solid interactions, which then can produce interesting structures, for example, twisted beams. And we have Bernard Hidding in the group who's looking at this method called the Trojan horse method for injection Anyway, you can speak to me after that to produce very high quality beams. But I'm going to finish by saying that we have this facility which we set up, which at Strathclyde, which is now running, which is based on a 350 terawatt laser, 5 hertz, which is now running, and a 40 terawatt laser at 10 hertz, which is the existing laser, and 7 beam lines. And so this is what will underpin any collaborations with you in India. Come and do work with us on this facility. This is what it looks like, and it's already been installed. The laser's running now, and it's running at 5 hertz. Actually, maximum power is 360 terawatts. And a lot of people are involved in this. A lot of people who have supported us in the past and current collaborators. And that's it. Thank you. Sorry about overrunning back a bit.
Hello, my question is that if we decrease the transfer size of the wake field, you can increase the quality of the beam, because that big problem to the beam emittance is the transfer size of the wake field.
Yeah.
If we can reduce the size of the wake field in transfer direction.
Yeah, you can, but it depends on the divergence. The emittance depends not only on the source side, but also on divergence. So from simulations, we know that the emittance is about 0.3 pi milliradian for our standard parameters. Our measurements show 1 pi millimeter milliradian, which is really restricted by the resolution of our system. So in principle, you could go, if you can, in the very last, one of the last slides I showed you, this Trojan horse method that one of my colleagues is working on. Use the ionization to control the injection. You can, if you get a smaller source side, of course you can go to a smaller emitter. So he claims to be able to go to emittances which are orders of magnitude below what we measure. But I think the complexity of this is huge, and I think this is, I would say, a medium-term project.
Because someone did the simulation, I think that theoretically possible, the wake field generation by the X-rays in a nanotubes, and find out the decrease the side transfer direction, increase the emittance of the beam, and get the high gradient in tera-electron volt per meter in nanotube. But in simulation, I think it's possible by the experimental.
Yeah, maybe you're right, that if you go to higher densities, use X-rays or whatever, you could then increase, because it all scales with the size of the structure.
Thank you. I'm talking about the electron injection into the bubble. My question is that because shape and size of the bubble is changing.
That's correct.
So obviously it may affect the electron injection.
That's right. That's what we've observed. That's our model as well.
At the time of injection, what would be the shape and size of the bubble that matters?
Well, it's evolving because the laser beam, it's a very complex process, because the laser beam is evolving because it's giving energy to the plasma. As Bob said, there's proton acceleration, proton deceleration. The quantum force is changing because that's inversely dependent on the frequency.
Practically, is it possible to control the shape and size of the bubble?
Sure, to an extent. You can control it with the plasma. Yeah. It depends on the history of the interaction. So you could control it with plasma gradients and so on, or the laser pulse transverse distribution. So there are ways of controlling it. I mean, people haven't investigated this very...
Because it definitely affect the electron injection. Means
sure.
The shape and size is very important.
Absolutely, yeah.
For the electron injection.
Yeah, not only the shape and size, but also the variation.
Yeah, obviously.
Of the shape, because that's what governs part of what governs the injection process. A bit of it is the sheath current. So if there's a bifurcation of sheath currents, then you're going to get a variation of the potential. So it's basically another way of controlling it. It's not just the shape. That's what we've shown. The shape and the velocity of the bubble is one factor. Another one is the actual sheath current. So if there's a bifurcation of the sheath current, that will modulate the potential. And
Yeah, there may be different factors, but shape and size may also be one of the factors.
No, absolutely.
Yeah.
Absolutely. Sure.
Can you show the X-ray spectrum that you just, it went a little fast for me, so.
Okay.
About 5 slides before. There was 2 X-ray spectra.
Yeah, getting there.
Maybe even this one will help. This one. Can you comment on the shape of the spectra? And what?
Well, these are measured. So the way these have been measured is by looking at Compton side scattering of wire that we had, because the photon energy is too high to directly measure it using a semiconductor detector. So what we did is downshifted the frequency using Compton side scattering, which also reduced the flux, and some of these are emission, K-alpha emission from the actual. This is cadmium telluride. This is the cadmium telluride detector. So these peaks here are from that. But this spectrum is just the synchrotron spectrum. Yeah, similarly, yeah, as well. So the fit is only really to the latter part of this. Okay. So we used both silicon detectors and cadmium telluride. Cadmium telluride is better for higher energies. So these are, the detector was called Medipix or TimePix. This is a standard detector used at CERN, for example.
You made a comment in between that particles are injected at an electric field which is much lower than the wave breaking limit. Right, one of yours.
That's correct.
Any comment on that? I mean,
yeah, it's just because the wave breaking is basically for the static situation. Okay.
Okay.
So, for those particular parameters, we are not at the parameter. We're not at the field for wave breaking. Okay. So there has to be something else which produces the injection. So one of these is the variation of the bubble shape or the bubble velocity.
Okay.
But what we've shown is that that's not sufficient. One needs also to include the variations of the sheath current.